And now it's time for Series and Parallel Circuits Part 2. To do this, you'll need your copy of Activity 6, since we're going to go over the details of Activity 6 and what we learned from it. Well, the big new addition in this activity was we used a multimeter to measure pressure differences using it as a voltmeter, and we used it as an ammeter to measure flow rate. Now, a voltmeter is a device that's used to measure pressure differences between its terminals, and the way we connected it is if you had a battery like this and you had a resistor, let's just draw one resistor, the way you would connect the voltmeter is you actually connect it in parallel. And the reason that you did that is you want to measure the pressure difference between here and here. So you connect the meter here and here so that the meter can measure the pressure difference between these two places. Pressure difference is measured in volts, remembering that the official science name for pressure difference is electric potential difference. You also discovered that a voltmeter is a high resistance device. Now the question would be, why does it need to be a high resistance device? And again, let's just think about if I have my battery here and I have a resistor or a light bulb, and I said I connected the voltmeter like this on either side of the resistor so I can measure the pressure difference, and it needs to be high resistance. And the question is why. So let's think about what would happen if it was low resistance. Well, then charges would go like this and they'd go around here, and if the voltmeter was low resistance, it would go through the voltmeter instead of through the resistor. And so if this was high pressure and this was low pressure and this was a low resistance, the voltmeter could be used to release this pressure. In other words, the voltmeter would affect the very pressure difference that I'm trying to read. So I need for this to be really high resistance so that I don't affect the pressure difference between these 2 points at all. So now let's apply our meters to actual series and parallel circuits and see what we find out. Principle we want to illustrate here is that in a series circuit, the pressure difference of the battery is divided up among the resistors. Now to do that, let's go to section 6.4 and see where we tested that. Now here's the diagram for section 6.4, and notice we had two batteries and they were connected in series to a long bulb and then to another long bulb. So that's really the circuit. All of these are just places to make measurements. So when we set up the voltmeter to measure pressures, we found out that we got about 3.0 volts here. Should get something like that, maybe 2.7, 2.8, depending on the age of the batteries, because we're actually measuring the pressure difference on either side of the battery. So we should get roughly 3 volts. Then when we looked at the pressure across the long bulbs, each of the bulbs individually, we found out that we got about 1.5 volts here and about 1.5 volts here, and the difference across both bulbs was about 3. Now this makes sense because if I was to color the circuit, I would color that red, and I would color it red all the way down to here, and it would be red all the way to here, and it would be red all the way to here. And then of course I can do the negative terminal of the battery, low pressure, and that would be all blue, and that would be all blue, and that would be all blue, and actually this would all be blue too, and I forgot to do that this would be all red. So that's, the reds are all high pressure and the blues are all low pressure. And in my circuit, red to blue is 3 volts because I have two 1.5 volt batteries. Now, because the long bulbs are exactly identical and there's 2 of them, you probably chose to color the wires in between the long bulbs as yellow, and that would make sense. So now what I have here is I know that red to yellow is 1.5 volts. Yellow to blue is 1.5 volts because it splits the red to blue of 3 volts in half. So I can see that the voltage of the battery, which in this case was 3.0, is equal to the voltage across the first long bulb plus the voltage across the second long bulb added together. Now the next thing that you did is we had another series circuit. So here's a battery to a long bulb and a round bulb. So now we have a series circuit with 2 unequal light bulbs. And we find kind of a pretty surprising thing. We find out that although the battery is still going to be close to 3, it's maybe 2.8, close to 3 volts, the long bulb, pressure across the long bulb is like most of it. It's 2.6, and this was like 0.2. Your numbers may be a little bit different, but what you should still see is that this number is most of this number. And in fact, this one, again, as it should be, is the sum of these two, of the 2 long bulbs, the 2 light bulbs added together. And again, if I color this, I'm going to get that that's red, and 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 that's red. And then again, I'm going to have, and that's blue, and that's blue, and that's blue, and that's blue, and that's blue. And now I have the decision, what color should this be? Remember that in a series circuit, the flow rate is going to be the same here, and the pressures divide up to produce the same flow rate. And this light bulb has a very large resistance, and this light bulb has very small resistance. So the pressures have to divide up in such a way as to make the same flow rate in a high resistance bulb as there is in a low resistance bulb. So I have to push harder in a high resistance bulb to get the same flow rate as I will in a low resistance bulb. So I need a high pressure difference here and a low pressure difference here. So what I'm going to go with is green. So if I make these wires green, then notice what I have is red to green is a big pressure difference. Green to blue is a small pressure difference. But I am noticing the same principle I saw before, which is that the voltage of the battery, which in our case is 2.8 volts, is equal to the voltage across the long bulb, which was 2.6, plus the voltage across the round bulb, which is 0.2. So, bottom line, whether I have the same light bulbs or resistors or different ones, this principle is still the same. The pressure differences divide up across light bulbs in series so that they add up to the pressure difference across the battery. So let's summarize. Basic principle. In a series circuit, the pressure difference of the battery is divided up among the resistors. Looks like this on your reference tables. Voltage of the battery is equal to pressure difference across light bulb 1 plus the pressure difference across light bulb 2 plus pressure difference across light bulb 3 added together. Now in the final part of section 4 of activity 6, we want to see what happens to pressures in a parallel circuit, and the basic principle is that in a parallel circuit the pressure difference across each resistor is exactly the same as that of the battery. So here we have 2 long bulbs in parallel. So here's the battery, and there's branch number 1 for the long bulb, and then in parallel we have long bulb in branch number 2. So these are 2 parallel branches, and what we did is measure the pressure difference across the battery, and you get, again, something like 2.8. And then when you measure the pressure across the first long bulb, you should get something very close to the pressure of the battery, and the same thing with this light bulb. And that makes sense because if I'm going to color this circuit, I have high pressure coming from the battery, goes right to the light bulb, goes right to the light bulb, goes to the voltmeter, goes to the voltmeter, goes to the voltmeter, If I then color the low pressure terminal of the battery, colors blue all the way up to the long bulbs, voltmeter. So notice everywhere in this circuit is red to blue, and in my circuit, because I have two 1.5 volt batteries, red to blue is 2.8, so both light bulbs see a pressure difference of 2.8. So this leads to our conclusion here that in a parallel circuit, pressure difference across each resistor is the same as that of the battery, and on your reference tables it looks like this. Pressure difference across the battery equals pressure difference across resistor 1, same as pressure difference across resistor 2, and no matter how many resistors or light bulbs I have, everybody gets the same pressure difference. Now we're going to talk about flow rates. So to do that, you switched your multimeter into ammeter mode. Now an ammeter is a device that you use to measure the flow rate through its terminals. So the idea here is that the ammeter has to be connected directly in series in the circuit so that you can measure the flow rate through it. So if I were to draw what I'm going to have here now, if I want to have, here's my battery, if I want to know the flow rate in a light bulb, I have to put the ammeter right in the path of the light bulb. So we would say that an ammeter is placed in series because if I put it around the resistor, I would be measuring the flow rate not going through the resistor. I want to measure the flow rate that's going right through the resistor. Charge flow rate, which is officially called current, is measured in amps. Now an ammeter has to be a low resistance device because again, if I have my battery, I'm going to do it wrong, so let's say I have a resistor here. So what would happen if I put the ammeter like this? Well, I don't want charge flow to go through the meter this way because notice what's happening? This flow is diverting around the resistor. But if I want to measure the flow rate going through the resistor, I don't want to give it an alternate path. So I want to put it in the same path like this so that everybody that's going to go through the resistor has to go through the meter. Now I want this to be a low resistance device because I want this to measure flow rate. Well, if it's a high resistance, it's going to lower the flow rate. I don't want to affect the flow rate that I'm trying to measure. If I have a high resistance device, then I will not get the same flow rate in this meter that I would get if the meter was not in the circuit. So I don't want to affect the flow rate by measuring it. So now we're going to use the ammeter to measure the flow rates in both series and parallel circuits. Let's see if this is true. In a series circuit, the charge flow rate, or current, coming from the battery is the same as the flow rate in each resistor. So in section 6.7 in your activity, you had the ammeter in various locations in a series circuit that had two long bulbs, and you were asked to make measurements of what the ammeter would read here and here and here. And I find these are just kind of sample numbers, roughly 46 milliamps here, and here I got 45 milliamps, which is pretty close. And then in the last circuit, I got another 45 milliamps. So it certainly does seem like the flow rate is the same everywhere in this circuit. Now I also tried another series circuit, where again there's two light bulbs, but now I've replaced the long bulb in that circuit with the round bulb here. Round bulb has a lower resistance. So let's see what effect that has. So in this circuit, this one was roughly 58 milliamps, which is a higher flow rate than in the top circuit. And here it was also about 58 milliamps. And here too it was 58 milliamps. So what I learned here is that in a series circuit, which is what these are, the flow rate is the same in all locations. Here, here, and here the flow rate was the same. I learned in this lower circuit that the flow rate is also the same everywhere in the circuit, but this flow rate is higher than this flow rate because this circuit has a lower resistance than the top circuit. So we have verified the principle that in a series circuit, the flow rate is the same everywhere. This represents the flow rate coming from the battery, and this is the flow rate in all the resistors or light bulbs, and it's the same everywhere. Now let's test this idea. In a parallel circuit, which has more than one branch, the charge flow rate that's coming from the battery is divided up among the resistors. Flow rates in a parallel circuit was tested in activity 6.9, which used this circuit. And I saw that the flow rate coming from the battery was about 107 milliamps, and the flow rate going into the battery was also about 107 milliamps. Going through the long bulb on the left, I had about 58 milliamps, and through the long bulb on the right, roughly 59 milliamps. And I can see that although 58 plus 59 is 117, and this was 107, and this is 107. You probably even got better numbers than I did, but that the flow rate going through these two branches adds up to the flow rate that is coming into them. So as the charge goes here, it splits. Some of it goes this way, some of it goes this way. Because the two long bulbs are identical, ideally I would have seen half of this flow rate go through this bulb and the other half go through this. So this number plus this number should have equaled that. And notice that once the flow from this long bulb and this long bulb join up here, this flow is the two flow rates from the long bulbs joined up together. So that is these numbers added together. And of course, that should equal that because we haven't made any new current. So we see that in a parallel circuit, the charge flow coming from the battery, which is represented by the I here, is divided up among the resistors. If I had 3 resistors, then I1, current in resistor 1, current in resistor 2, current in resistor 3, when added together, equals the current coming from the battery. So we're going to summarize using the formulas on the reference tables. In a series circuit, the flow rate is the same everywhere. Battery, all the light bulbs, because there's only one path for the charges to move, so everybody has to go through everything. However, the pressure difference across the battery divides up among the resistors to produce this equal flow rate. So high pressure differences are needed for large resistances, less pressure difference needed for lower resistances. So the pressures divide up to get the same flow rate, but if I add all the pressures together, I get the pressure difference of the battery. If I have more than one resistance, the equivalent resistance is equal to simply the sum of the resistors added together. In a parallel circuit, which has multiple paths, multiple branches, the current coming from the battery is equal to the current in each of the branches added up together. The pressure is the same everywhere in a parallel circuit. Each one of the resistors gets the same pressure difference. And I also learned the way to determine the equivalent resistance in a parallel circuit with this formula. So that's series and parallel circuits, currents, voltages, resistances.